Hello and welcome to the Isaac Newton Institute podcast with me, Kira Dangerfield, the Development and Communications Coordinator here at INI. On today's episode, I speak to Dr Robin Thompson from the University of Oxford. Robin is an epidemiologist and has been doing modelling work around COVID-19. In today's episode, we talk about the data behind the models and how this data is used to help inform parameters in the models that are used to understand the spread of COVID-19 at the moment. I hope you enjoy and let us know what you think. Cool, right, so thank you very much, Robin, for joining me today. So I'd like to welcome Robin Thompson to the show today. He is a Junior Research Fellow in Mathematical Epidemiology at Christ Church, University of Oxford. His research involves using mathematical models to understand how diseases spread so that forecasts can be made and control interventions can be planned with more precision. He has previously worked on modelling Ebola outbreaks and more recently modelling COVID-19. So thank you very much, Robin, for joining me today.
Thanks, Kira.
So the last episode, I spoke to Kit Yates, who I think you know.
Yes, that's right, yeah.
So he gave a sort of overview of the type of mathematical models that are used, the mathematical techniques, and some of the challenges. So he in particular raised the point that, as with all biological systems, it's quite one of the biggest challenges that you guys have is the fact that the data is often quite messy and incomplete. So I wanted to kind of explore that a little bit more with you today, and particularly in the context of the models that you're currently working on and trying to develop for COVID-19. So
Yes,
I guess just as this is quite an open-ended question, so feel free to kind of go with it how you want. But what types of data do you have available to you as an epidemiologist? And how are you using these data sets to try and parameterize and validate the epidemiological models that you're building?
Yeah, so there are loads of different types of data that are available, and also, of course, lots of questions that modelers are interested in answering related to COVID-19. And so lots of different types of models are developed to address the different questions and use all the different types of data. So I guess the first type of model that immediately comes to mind are the population scale models that we've been hearing about a lot in the news over the last few weeks. And typically those types of models are used to predict the numbers of cases and the numbers of deaths that we're likely to see, and to look at things like when the outbreak's likely to peak and that sort of thing, and then to test the possible effects of different control interventions. And so the outputs of models like that are time series for the numbers of cases and the numbers of deaths. So, for example, the numbers of new cases that we're likely to see every day, or the numbers of deaths that we're likely to see every day. And so in order to use a model like that, the kind of data set that you need is data describing exactly those two things. So data describing the numbers of cases per day in different countries around the world, data sets describing the number of deaths per day in different countries around the world. And those types of data are useful because you can take your model and you can then tune the model parameters, so use statistical inference techniques to tune the model parameters so that the output from the models match exactly those observed data sets. So that's kind of the most kind of obvious type of data that's available, data on the numbers of cases and deaths per day. But there are also lots of other types of data sets that are used in conjunction with other types of model. So something that I've been working on recently with researchers at the London School of Hygiene and Tropical Medicine are renewal equation models that are based on branching processes. And the idea there is to look at how transmissibility of the virus that causes COVID-19 is changing in different countries around the world, and how it's changing in response to different interventions that are being implemented. And so for that, you need a similar type of data. So you need data on the numbers of cases per day in different countries, but you also need an estimate of what's called the serial interval. So the serial interval is the time between successive cases in a chain of transmission. So if I start to show symptoms and I infected someone else, then the serial interval is the time between me showing symptoms and then the person that I infect showing symptoms. And so we need an estimate of what that time period is, or what the distribution of those times are between different infections. And so for that, what we need to know is we need to know the timing of symptom appearance in an infector and the timing of symptom appearance in a recipient. And so for that, you could use a data set, for example, from a household study where you can assume that one person has infected someone else in the household, right? And if you know when those individuals show symptoms within that household, then you can work out the interval between the infector and the recipient showing symptoms. So that's another type of data set. And there are loads of other different types of data set out there that can be used for answering different questions about COVID-19. One thing that I looked at very early in this epidemic, prior to the virus coming to the UK, was, what is the probability when the virus comes to somewhere like the UK or another country of then seeing a major outbreak in that country? And the key question, the key quantity that affected the behavior of that model was the time between an individual showing symptoms and then being isolated. So if you can isolate someone very quickly after showing symptoms, then what we found in the model is that reduces the chance of there being a big epidemic from that single imported case. And so again, that's a different type of data that we needed. That's data describing, when people show symptoms and then when they're subsequently hospitalized and isolated. So again, a different type of data set that we used. So huge numbers of different types of data sets exist, and they're very useful for answering very different questions about COVID-19.
And just to pick up on that first point about the statistical methods that you're using, are they typically things like Bayesian type methods, so like ABC, or just?
So it's actually
what kind of approaches?
Yeah, so it's kind of a mixture, and actually the approaches that we're using are different, again, in the different models. So I mentioned briefly a method that we're using to estimate the reproduction number based on renewal equation models. So actually there, what you can do is you can write down an expression based on cases that have been seen previously for the probability of seeing a certain number of cases today, given a value of a reproduction number. And then what you can do is invert that. So you can actually write down a likelihood for the reproduction number. And so you then have a likelihood-based method for estimating disease transmissibility in real time during an outbreak. So that's one type of inference. Other models, so the kind of population scale models, tend to use sort of MCMC techniques, or ABC, like you just mentioned, to estimate model parameters from time series data on the numbers of new cases per day or deaths per day. So it really varies based on the different models.
And so the branching process stuff you were mentioning, it sounds really interesting. I'd not heard about that before. Just so that I can put in the show notes, do you have some papers and things? Have you guys written some papers on this, or how far along are you in the?
So the idea there was actually right back at the beginning of the current pandemic. So the idea was, we've got an outbreak going on in China. What is the risk of getting an outbreak happening in the UK, for example, or other countries around the world? So I think certainly from the UK's point of view, that's now a question that's no longer kind of that relevant, but it was very relevant right back at the beginning of the outbreak. And so I wrote a paper published in the Journal of Clinical Medicine called, I think it was called something like Novel Coronavirus Outbreak in Wuhan, China. Intense surveillance is vital for preventing sustained transmission, I think, or something like that. So it's published in the Journal of...
I'm very impressed that you can remember that long title.
It may not be right, but it was along those lines.
Cool. No, and I'll put a link to it in the show notes if you let me know.
Okay, great. Yeah, sure. I'll send that over afterwards.
So no data set is ever perfect, as Kit touched upon in the last episode. So what are some of the issues with the data that you're currently using for these epidemiological models?
You're absolutely right that no data set is ever absolutely perfect. And at the moment, there are a few specific challenges. So one of those is that if you want to understand the effects of different control interventions, the thing that you really want to be able to track is you want to be able to track the number of infections happening each day and how that number of infections is changing through time. And the reason that's important is that if you put on a new intervention, so you introduce some new control measure, and then transmissibility stays the same or transmissibility increases, then it suggests that that new intervention isn't doing a great job. Whereas if you put on a new control intervention and then transmissibility comes down again, then the intervention is doing a pretty good job. So what you want to be able to see is you want to see the numbers of new infections per day, but in reality, that isn't really what you see. So what you instead see is you see the numbers of reported cases every day. And so there's a delay between an infection happening and then someone showing symptoms. And then there's a further delay between someone showing symptoms and then reporting as a case. And so that delay makes it pretty hard to assess the current situation because we haven't actually seen all infections yet, right? There are these delays between infections happening and then subsequently appearing in our data. So that's one big challenge. Another one is that, even if you've got good quality data on symptomatic cases, so reporting is not ever going to be perfect, right? Some people for COVID-19 experience mild symptoms, they recover at home, and they never appear in the data sets that we're using for forecasting. We probably all know someone at the moment who said, actually, I think I'd contracted the virus before, but I'm not sure because I was never tested, and my symptoms were quite mild. So that's another big challenge. Reporting means that we simply don't see all the people that are currently infected, even with a delay. So they're two of the kind of big challenges at the moment.
And how are you guys sort of taking into account these deficiencies in the data sets with regard to the predictions you're making, and in particular how these deficiencies might be affecting the uncertainty around your predictions?
Well, so if we know that there's a kind of deficiency in the data set, if we know exactly what that is, so for example, we know that there's a delay between symptom onset and reporting, then the best thing that we can do is we can actually build that sort of systematic deficiency into the model that we're using. So specifically considering that delay between symptom onset and reporting, what you could do is you could look at data on reported cases, then you can kind of back calculate the times of symptom onset. So and you might not know them exactly, you might get some distribution, but nonetheless, right, you can back calculate when symptom onset happened from the data on reported cases. And then if that's the thing you're interested in, you can then perform inference on that back calculated data set. So the best way to handle any sort of deficiency like that is actually to build it into the model. And as you referred to, you'll get some corresponding uncertainty with that, but it will actually be physically sort of built into the model that you're using. The other thing that you can do is actually consider whether there are other sources of data that might be more reliable. So if you've got a data set that you know has deficiencies, maybe there's an alternative data set that you can use that might not have the same issues. So as an example of that, if you take data on cases, well, that's likely to suffer from underreporting, like I was saying a moment ago. So perhaps there are other data sets out there that you could use instead that might be less likely to suffer from that underreporting. So for example, you could parameterize your model to match data describing the numbers of deaths per day instead of the numbers of cases, because deaths are more likely to be reported correctly. As we've seen in the UK over the last few days, even data on deaths is not reported perfectly. Deaths in hospitals are much more likely to be reported than deaths in care homes, it's turned out. But nonetheless, I think data on deaths is much more likely to be reliable. So time series describing the numbers of deaths is going to be more reliable than time series describing the numbers of cases because of underreporting of cases. And then the second part of the question was that about uncertainty?
Sorry, just picking up on...
Yeah, sure.
So just picking up on the point about the data you can use for cases. So I know I think for the 2009 epidemic, the swine flu epidemic, they subsequently looked at whether they could use calls to 111 to try and get a better estimate of case numbers, because they would then, look at what people were reporting symptoms, and then they could, say, well, maybe that was a case. Do you know if anything like that is being used for the current epidemic? Because I guess I'm just thinking that initially they did ask everyone to always phone 111 rather than see their GP. So I don't know. It was just a question.
So specifically on the 111 point, I'm not sure whether that's happening, but certainly a similar principle has happened at different stages of this outbreak, where individuals have taken, or modelers have taken, data which might be assumed to be more accurate and then sort of calculated the expected number of cases given the more accurate data. So one example of that was right back near the beginning of the current outbreak, where there was significant uncertainty on the numbers of cases in Wuhan in China. And so what I think the group at Imperial did at that point was they took data on the numbers of cases on flights coming out of China, out of Wuhan specifically, and then used those data to kind of say, well, how many cases would we expect there then to be back at the source using a probabilistic model. So certainly that idea has been used. I don't know specifically whether they're using the 111 data to do that. I know another option is internet search engine kind of searches, based on the number of people that are searching for a particular thing, you can sometimes infer how many cases there might be. I guess given how big news the coronavirus is, though, I suspect that might be challenging at the current situation, because people might Google coronavirus symptoms now while not necessarily displaying any of those symptoms themselves. But certainly that sort of thing has been happening during this outbreak for sure.
Cool. That's very interesting what the Imperial Group are doing or have done. Sorry, I cut you off. But I was just wondering how you sort of account for these in the uncertainty around your predictions.
Yeah, so I guess the main thing to say there is that there's a huge amount of uncertainty in any model prediction. Most simulations of models generate a wide range of possible future outcomes. And that can be based on a number of things. But one thing it can be based on is simply randomness between different simulations of a model. If you have a stochastic model and you run it multiple times, you're going to get a range of possible future outcomes. But another thing it can be based on is uncertainty in the values of disease transmission parameters. And so again, what you can do is you can run lots of simulations of your model with different sets of plausible parameter values. And again, you can explore the huge amount of uncertainty and what's likely to happen going forwards. And this can make a really big difference. So one example of that is that in one of the models used by the London School of Hygiene and Tropical Medicine, what they found is that over multiple simulations, then on average, if there are absolutely no control interventions in the UK, their model predicted that around 85% of the UK population would at some point end up contracting the coronavirus. But when they accounted for uncertainty and the randomness between different simulations, they actually found that the range was actually pretty substantial for the numbers of individuals that could end up being infected. And actually the range was 68% up to, I think, something like 96%. So that range corresponds to over 16 million people. And so it's really important that ranges like that are communicated by modelers. There's a huge amount of uncertainty. No model can tell you precisely how many individuals are going to get infected. And so reporting confidence intervals like that over multiple model simulations is really very, very important. It's a big range, and that's an important point you make about the uncertainty that we have around model predictions. Now, my final question is maybe slightly tangential, but kind of picks up on this idea of data and what data is being used to inform the models. And it's partly because, recently in the news, there's been quite a lot about the need to ramp up testing, and we need to test more, and how the government are trying to do this. And obviously, the government control policies are being heavily guided and influenced by mathematical models. So I kind of feel that there's a connection there, because to me it would seem that the more widespread testing there is, the better the model predictions are, the better guidance they're able to give. So, do you think widespread testing is really important, not just for us to know how many people have the disease, but also to help improve model predictions? I think that is it depends, and it depends a lot between different models. So the UK currently has an aim of 100,000 tests per day, I think, by the end of this month, which is that tomorrow. So that was one of the UK's kind of aims. And obviously, if that was implemented, for some models that would be really helpful, because it would tell us more precisely how many individuals are currently infected. So in other words, if you're looking to make a forecast where what you do is you simulate forwards from the current time, the initial conditions of that forecast would be more accurate. and therefore you might expect the forecasts to also be more accurate. So for a kind of forecasting model like that, then it might be expected that more widespread testing will improve model predictions. It certainly isn't always the case, though. And the reason for that is that, so I talked a bit earlier that one of the things I'm doing is looking at estimating the reproduction number. So the number of individuals that each infectious host is likely to go on and infect. And we're estimating changes in the reproduction number through time. And if it's the case that that the proportion of individuals you detect remains constant through time, then estimates of the reproduction number can be quite robust. I guess to give you an example, let's suppose that we have a population with 5 people, and sometime later those 5 people have generated in total 15 infections. Then I guess your estimate for the reproduction number would be an estimate of about 3. But if we tested more people, maybe instead we'd seen, initially there were 50 infections and 50 infected individuals, and they go on to cause 150 infections in total, then you would still get a reproduction number of 3. Where the thing that will be challenging in that case, though, is if the proportion that you're testing is something that changes in time, because then it would be really hard to say precisely how many individuals each infectious host was going on to infect, right? That's when your estimates of the reproduction number wouldn't be quite so robust if your testing practices are changing. So actually for some outputs of models, it might make it more challenging if the numbers of individuals that we're testing is going to be something that changes through time to make kind of robust inferences. I think the answer to your question is, in general, yes, absolutely, test more people. You get a better picture of what's going on, and therefore your forecasts are more likely to be accurate. But there are some situations in which you would then have to account for changing numbers of individuals tested in the models if you want to make robust inferences.
No, that's really interesting and an important point. It reminds me about work that I did in the past on modelling chlamydia and how they brought in a national chlamydia screening program, and that hugely ramped up testing. But if who you're testing, and if it's not just sort of random sample testing, it can affect how you how you're building that into your model. And so it's important to.
Absolutely, and I guess even if it is
to take it into consideration.
Yeah, absolutely. And even if it is random testing, I guess if you suddenly increase the numbers of tests you're deploying, and the only output you get from that is just seeing more cases, it could look like disease transmissibility is increasing, but that could just be because you're seeing more of the cases. It's not, it's not that actually more cases are happening. It's just you're seeing more, and so your estimates of transmissibility would go up through time, which isn't necessarily a reflection of what's really going on.
Yeah, no, that's an important point. Great. So the final question I have, well, it's not really a question, it's really about this Royal Society Rapid Assistance in Modelling the Pandemic Initiative, which I think by the time this episode comes out will have been all announced. So I know that you're kind of involved in this initiative from Oxford side, and so I just wondered if you could give a brief description about as much as you know about it and exactly what your part of it is involved in Oxford.
Yeah, sure. So the idea of this RAMP initiative is to inform the UK government's response to the ongoing pandemic by engaging more people that have mathematical modelling expertise. And it does this in a number of different ways. So one way, for example, is to train modellers from a range of different backgrounds in epidemiology. And that means that, because those modelers have lots of different backgrounds, they might be able to provide novel insights into existing data and models to then inform the work of government scientific advisors. So that's one of the things that RAMP is trying to do. My role in RAMP is a little bit different. So we're providing a rapid review service for the government advisory groups for SPI-M and for SAGE. And the idea is that we're reviewing a lot of the modelling analyses that they're using to then make recommendations. So my specific role is leading one of the sections of this rapid review service to make sure that the recommendations are based on kind of the most rigorous possible science.
That's really important, because obviously the review process normally takes months, years, but it's important that these papers are being reviewed before they're going to inform policy and not just being put on archive.
Yeah, that's absolutely right. And so actually for this particular rapid review service that we're providing, there are kind of 3 categories of urgency. But the most urgent one is that they're expecting reviews to be returned within 12 hours. So yeah, like very, very fast paced and very, very quick turnarounds. I should say though actually that modelers around the UK are doing everything they can to try and help at the moment, and so actually this ramp initiative is only just starting, but we certainly haven't been short of volunteers who are willing to, expert modelers who are willing to review papers for us.
Well, that's good to hear. No, I think there is a real appetite from the community to just try and do whatever they can, but I guess it's important to try and do that in a coordinated fashion, and I think that's kind of part of this ramped call, to make sure we're coordinating and it's not just a load of sort of scientists potentially reinventing the wheel every time.
Yeah, absolutely.
So just to wrap up, I just have a few sort of more fun kind of questions. So is there one epidemiologist or maths communicator who you would recommend to follow on Twitter?
That's a good question. So I think probably I would say maybe Adam Kucharski at the London School of Hygiene and Tropical Medicine.
That's who Kit said as well.
Oh, nightmare. I think it's hard to look beyond him because he's providing a really thorough narrative about the role of mathematical modelling in decision making for COVID-19, and he updates it very frequently. So I think if you want an epidemiologist or maths communicator looking at infectious disease modelling, I think it's hard to go beyond Adam.
Well, there we've got 2 recommendations here, so he's definitely someone. People...
He must be good. Yeah,
that's fine. And do you have a book recommendation if someone wants to get up to speed on the mathematics behind these models?
So the book that I normally recommend to my students is Modelling Infectious Diseases in Humans and Animals by Keeling and Rahani. So that's a textbook that's pretty, it's quite approachable, and it covers a wide range of different types of epidemiological modelling. The other thing to say, though, is that, obviously getting hold of a book like that now might be quite challenging. So there are lots of other resources out there that people can look at. So one example might be public lectures online that can provide a sort of an overview of epidemiological modelling techniques before necessarily then diving into the details in a textbook.
So, for example, you did a public lecture, right, for Oxford University a few weeks ago?
Yeah, that's right. Yeah, that's right. Yeah, so about 2 weeks ago. So that is now available on YouTube. I think it's also on the Oxford Maths website. That might be one place to start. But I'm sure that there are other public lectures about epidemiological modelling out there too, that will provide a pretty good introduction to the field.
But yours was very good, so I will make sure that I will put a link to in the show notes, because I thought it was very good because you actually give examples in the context of COVID-19.
Thank you. Yeah, cheers. I kind of tried to build it up as well from kind of how a modeler might start, and then how a modeler might then refine the model to then hopefully make more accurate and more kind of policy relevant predictions.
And I knew you were going to pick Keeling and Rahani because you were always stealing that book when we were in the lab together. So Robin and I, he was a PhD student when I was a postdoc in the same lab, and he was always stealing my copy of Keeling and Rahani.
And I probably still have it.
No. When I went on maternity leave, I was sure to lock it in my desk so that it didn't get lost.
Very well played.
And sorry, just a final question, I guess. As a community, what do you think we can be doing as mathematicians to support the mathematical modelling effort?
Yes, that's a good question, and a question that I think lots of mathematicians are asking. You alluded earlier to the fact that perhaps reinventing the wheel isn't the thing to do. I think there are over 1,000 preprints and published modelling studies now about COVID-19. So developing another one of those maybe isn't the best thing to do. But there are lots of ways that mathematicians can help. So one way, if a mathematician has expertise in this area, might be to review manuscripts for journals. Another might be to read existing manuscripts about COVID-19 and then promote the ones that are most reliable and are most rigorous. Because, like I said, there are over 1,000 studies out there, and so it's really important that the ones that kind of everyone then goes on to hear about are the ones that are the most reliable. So that would be something that would be good to do. If a mathematician does want to help by doing modelling, I think my advice might be to not focus on the kind of standard population scale questions that epidemic modelers often address. So, taking the scale of a country, for example, and then making a forecast and predicting the effects of different control interventions might not be one of the most useful questions to focus on, because lots of epidemiological modelers are doing that already. But there are lots of less well-studied questions that maths can be used to address. So, questions, there's a huge range, but questions like how should businesses respond to COVID-19? How can supermarkets best be arranged to minimize the number of contacts that people have? That sort of thing are all the kinds of questions that quite fundamental maths can be really useful at addressing. One way to do that, obviously, is to write papers. Another way is that there are some virtual study groups being set up to address mathematical questions related to COVID-19. So in the UK, you can look on the Newton Institute website. You can also go to the International Centre for Mathematical Sciences website. So I think that's icms.org.uk to find out more about these virtual study groups. So I think there's some of the things that mathematicians can do, and there's certainly a lot of scope for mathematicians and mathematical modelers to help in the COVID-19 response at lots of different levels.
That's really good advice. And the I&I are involved in some of these virtual study groups along with our partners, the Newton Gateway. So I will make sure there are links to those relevant resources in the show notes. So just to wrap up finally, I realised I should let people find out where they can hear about you, and so what your Twitter feed is, and
yes,
and your
my Twitter
website.
So my Twitter feed is at Robin N Thompson, and my website is robin-thompson.co.uk. Specifically, I guess the most useful part of that website is probably the list of publications, because that includes the kind of more recent publications that we've put out there about COVID-19.
Great, thank you very much, Robin, and I'll put links to all of that in the show notes for people.
Perfect, thanks, Kira.